All right, we're going to be looking at approximating areas with some Riemann sums. So I always say calculus is in two parts, a going forwards and a going backwards. The going forwards is like the derivatives and finding these rates of change. And then the going backwards is like undoing all of that. So we're in the going backwards part. And so instead of finding slopes of graphs, we want to find areas under the curve. So I'm going to do a scenario first here. So in order to avoid floodwater entering the house, we have a pump that for the first 8 hours pumps at a rate of 500 gallons per hour. And then the storm, that should say storm, gets stronger. We get a second pump. And for the next 16 hours, we remove 900 gallons per hour. So let's kind of draw a picture of that. So our x-axis is our time in hours, and then the y-axis is going to be the like the amount of water, and that's in gallons, right? So if we have a graph of gallons per hour, the first 8 hours we can pump at 500. I'm going to put an open circle here because once we hit that 8 hours, we have that second pump going 900. Right? Okay. And so there's our picture of our graph. So when we say area under the curve, we're looking at the area between the graph and the horizontal axis. So in this case, that x-axis. So we want to find the area under the curve for that first 8 hours. So I'm just going to make a little box here. We're going to find that area. It's a rectangle, right? So area of a rectangle is length times width. And so we have a length and a width. One of them is 8, and the other one is 500. So we have an area of 4,000. And this would be in gallons of water for that context of the problem. Because if we think units, we're doing 500 gallons per hour for 8 hours. So those hours units will cancel out, and I'm just left with gallons, right? Find the total area for the entire 24-hour period and explain the context. All right, so I have the area of that first chunk. So now let's just find the area of this second chunk, right? So go in blue. We already know we have that 4,000. And then this other one, our length and width, we have a length of, it doesn't matter whether it's the length or the width, but one of them is 16 and the other is 900, right? So if we do 4,000, and then I gotta get a calculator for that one, 16 times 900 is 14,400. So we have a total of 18,400. It still is in that units of gallons of water. So in terms of our context, this is gallons of water, I guess we should say removed from the house from this storm. All right. So we can think of these areas. So a basic overview of doing these areas is we can do these areas as a limit. So, I've been making those rectangles. So in the limit of rectangles approach, we take the area under the curve within a certain interval by making a bunch of rectangles. And they're either inscribed or circumscribed to the curve, right? And the more rectangles we use, the better the approximation is. So if we, make the number of rectangles go off to infinity, then we get, the best area we can get. And doing all of that is known as integrating. But using the rectangles and approximating the area is what this Riemann sums is. Because we are taking these rectangles and we are adding all the areas up. So we're summing the rectangles. So let's look here. So consider a 30-gallon aquarium is being filled with water at a rate modeled by this function here, where t is in time in minutes and r of t is the gallons per minute. So find the volume of water in the tank after 5 minutes by using 5 rectangles that are 1 minute wide and r of t in height. So, do we see we got 5 rectangles here? 1, 2, 3, 4, 5. Right? So we want to add up all the area. So I'm going to call this 1, 2, 3, 4, 5. Make it easy. So we want to take the areas of all of them. So adding them up. Right? They all have a width of 1. Right? And then their length is going to be the function value, right? So I'm going to go off to the side and plug these in. So my function is 6 sine of pi over 8t. And I want to evaluate at 1, 2, 3, 4, and 5. So at 1, I get, and I'm going to round, it doesn't say, so I'm going to do 2 decimals. So 2 point, let's see, it's 296, so that actually would round to 2.3. Let's do 2. It's going to round to 4.24. If I do 3, I get 5.54. If I plug in 4, I get 6. And if I plug in 5, I get 5.54. All right, and then this is just something to notice. These rectangles are all going to have the same width, right? They all have a width of 1. So I can factor that out. And then I can do all these areas, or these lengths, and add them. So 2.3, 4.24, 5.54, 6, and another 5.54. So if I add all those up, 2.3, 4.24, 5.54, 6, and another 5.54, I get about 23.62. And this would be in gallons. That's how much we have. It's just in cubic gallons because it's in volume, but all right. And so if we want to write this in an integral notation, because we're eventually going to be doing integrals anyway, whoops, this is what it would look like right here. All right, we can do the limit of adding up an infinite number of rectangles, and what that gives us is this definite integral, which is right here from 0 to 5, the integral of r of t dt. And we'll get into that a little bit later. So I'm going to look at a few different types of Riemann sums. So for these rectangles, there's 3 kinds. We have a left endpoint one, which in this case, for this function, it would be an inscribed rectangle, where we're making our rectangles and we're using the left end point of those rectangles. Right? Or we could do a right-hand sum. So in this function, this is a circumscribed rectangle, and we're doing the right end point of those rectangles. And then we have one that's the midpoint. And we would make our rectangles, and then we would pick the midpoint of those rectangles. Okay? So let's piece apart this definition here. So let f be continuous on an interval a to b, and the function is greater than 0 for all x in the interval. So let a to b be partitioned into n subintervals of equal length, where the delta x, which is the width of the rectangle, is b minus a all over n. Then the definite integral of f over a to b is, so the area would be equal to the limit as the number of rectangles goes to infinity of the sum of all the rectangles, right, with the function value, which is the length, and then the change in x, which is the width, and that is all equal to this definite integral here. The integral from a to b of f of x dx. All right. So for right now, we are summing all of the rectangles. Okay. So find the area under the curve of the function 1/2 x plus 1 on the interval 0 to 5 using geometry. Let's see if we can draw this. So I'm going to do my best. So we want from 0 to 5. So I could find all that. So 0, 1, 2, 3, 4, and 5. If I plug in 0, I get 1. If I plug in 1, I get 1.5. If I plug in 2, I get 2. You see what's going up half a step. If I plug in 3, it's 4.5, right? If I plug in 3, 1.5 plus 1. I don't know why I said that, because that's 2.5. If I plug in 4, that's 2. 2 plus 1 is 3. And then this one is 3.5. So I can try and plot that. Or I could have gone from plotting functions. I have a y-intercept of 1. And then I have a slope of 1/2. So up 1 over 2. And up 1 over 2. Do my best here. Right, and then geometry-wise, if we're looking from 0 to 5, right? Look at this shape here. Trying to do my best to draw it. Right, let's think of our quadrilaterals, right? This is 4 sides. So it's not a square, it's not a rectangle, it's not a rhombus, not a parallelogram. It probably starts with a T. Trapezoid. And I hope you remember from your elementary school learning the area of a trapezoid, right? 1/2 the height times base 1 plus base 2. So 1/2 the height is 5. Base 1 is 1. And base 2 is 3.5. Sorry if I try and multiply that. That's 5 halves. And then that's 4.5. 4.5 is 9 over 2, which will make 45 over 4. We don't have any units here, so units squared. So it's nice when our function makes a nice shape that we know the area formula for. And then I hope you could kind of visualize in this here that we have some errors, I guess you could say, in the sums. So like this first one, this left-hand one in this function, we're missing some chunks here, right? So this would be an under approximation. And then for the opposite reason, we have stuff above our curve. So we have extra area there. So this right hand for this function here is an over approximation. And so in this little chart here, I'm just going to give you whether it would be an over and under based off the type of function it is, or like the behavior of it. So if we're concave up and increasing, we're looking something like this. So if we do a left-hand sum, so, all right, I make a rectangle and I use the left points, right? That's going to be an under approximation. And if I go the other way and do right hand, then that's going to be an over approximation. Right? But if we're concave down and increasing, that looks like this, concave down and increasing. Left hand is still going to be an under approximation, and the right hand will still be an over approximation. But then when we switch to decreasing, so concave up and decreasing looks like this, then this is where it switches. The left hand is now going to be an over approximation, and the right hand is going to be an under. And then decreasing and concave down looks like that. Left hand will be over and right hand will be under. All right, feel free to draw some scenarios for yourself and see what I'm talking about here. Or we just have this chart. That way you know whether it's going to be over or under based off the shape. All right, so let's do some calculations from a table. So this table below represents the velocity in feet per second of a car traveling on a straight road over a 50-second time interval. So we're going to do a couple sums here. So estimate the total distance traveled by the car using a left-hand sum method, L5, with 5 partitions of equal length. So you might see it shorthanded like this, L5, R5, T5, M5, for all the different types. You know, the right, the left, midpoint, and there's a trapezoid rule as well. So the little subscript tells us how many partitions there are, and we're always going to have partitions of the same length. Right? So from 0 to 50, to find that, I know it was earlier in this section, to find that change in x, or that change in width, that was b minus a all over n. So our interval is 0 to 50. Oops. So 50 minus 0, and then we want 5 partitions, and then 50 over 5 is 10. So I'm going to draw little rectangles here on my table. So from 0 to 10, we'll make one rectangle. From 10 to 20, 20 to 30, 30 to 40, 40 to 50. And then I always check, make sure there's 5. 1, 2, 3, 4, 5. So we're good there. And we want to do the left sum. So what that means is we take the left endpoint. So between these two, we got 0 and 10. The left endpoint is 10. And the rectangle that's 10 and 20, the left hand is 20. And then so on and so forth. 20 to 30, we got 52. 30 to 40, 80. 40 to 50, we have 77. So I can add up all of these rectangles, right? Length, width, etc. Or they have the same width across the board, right? And that's the width of 10. So I can factor that out. Sorry, I paused my screen on my end. And so I remember the last thing I said was we can factor that 10 because they all have that width of 10. And then we can just add the others. So 0, 20, 52, 80, and 77, right? And so if I do that right quick, that's going to give me 2,290, all right? And so since we went from a velocity to a distance, this is just in feet, all right? Now we're going to do a right-hand sum. So this time I'll do it in red. Same rectangles, but we're going to use the right endpoints this time. Okay, so it has the same width of 10, but I'm using the right endpoints this time. So 20, 52, 80, 77, and 74. And so if I add all those and multiply by 10, I get 30, 30. All right, a midpoint. So it still has a width of 10. But we're going to use the midpoint. So it just happens to be that the midpoint between 0 and 10 is 5. The midpoint between 10 and 20 is 15. We have the values of the midpoint. We don't have to find what it is. So then we can add all of those up. So it was at 14, 28, 70, 86, and 70. So if I do all this math, I get 2,680 feet. Okay. So now a trapezoid. This one's a little interesting, right? Because remember the area of a trapezoid is 1/2 the height, and then base 1, base 2. So half the height is going to be the same for each trapezoid. So I can factor that out. All right, and that height is that width, so 10. And then I just need to add up all of the bases. So I'm going to do something weird here, right? So we have these two endpoints, right? So this is base 1, base 2. But then when I go to the next rectangle here, the 10 and 20, base 1, base 2. 20 and 30, base 1, base 2. Base 1, base 2. Base 1, base 2, right? You see my little tally marks? I've got 2 of them at 20, 2 of them at 52, so on and so forth. So the endpoints, the 0 and the 50, only count 1 time, and then the rest in the middle count twice. So when I go to write my little thing here, I've got 0, and I have 2 times 20, 2 times 52, 2 times 80, 2 times 77, and then 174. And so if I type all of that into a calculator, I get 2,660 feet. Right now we want to find the average of the left and the right and compare it to the trapezoid. So we know the trapezoid is, we just did it, the 2660. Right, the left and the right, well, the right was 30, 30. Average is we're going to add them up and divide by how many we have. So we have left and right, so we have 2. And then the other one was 2290. It's 2290. So if I do that average, 30, 30 plus 2290, and divide that by 2, I get 2660. Very interesting. The average, the left and right, is the same as the trapezoid. So it's crazy, right? All right, so we've done it from a table, we've done it from a graph. Let's do it from a function. So let ln denote the left endpoint sum using n sub intervals and r sub n being the right endpoint sum. Compute the indicated sum for the given function over the indicated interval. Round decimals to 3 places. All right, so we're looking from 2 to 6, and we want r6. So what I like to do is I don't have my values, so why don't I find them? And let's figure out what we want. We know we're going to have 2 to 6, and we want 6 sub-intervals. So to find that width, right, we'll do 6 minus 2, and then all over the 6 intervals that we want. Or 6, yeah. So that's going to be 4/6, which is 2/3. Right, so what I'm going to do is I'm going to turn these into fractions. So instead of 2, I'm going to write 6/3, just so I can add 2/3 pretty easily. So 6/3, 8/3, 10/3, 12/3, 14/3, 16/3, and 18/3. And then I have my 6 rectangles, right? 1, 2, 3, 4, 5, 6. And now I just need the function values. So it's 1 over x times x minus 1. Okay, so I'm going to go into a calculator here and define that function. So the function is 1 over x times x minus 1. And let me just plug in these values here. So we'll do the whole numbers first. So 2, 4, and 6. And now we'll do the fractions. 8/3. And then 10/3. 14/3. 16/3. Okay. So we know the width of the rectangle is 2/3. And then we want the right endpoint for all of these. So I'll just circle it in a different color. 1, 2, 3, 4, 5, 6. And then we'll just add all those up. And let's see what we get. 0.225 plus 0.129 plus 0.083 plus 0.058 and 0.043 and 0.033, and then we'll times that by 2/3, and I get about 0. We can round that 381. All right. And then that is all for the Riemann sum section. So if you have any questions, let me know.